Hi, this is Ms. Basin, and today we're going to talk about oxidation-reduction reactions, which is section 4.4. So the first thing we need to do is define what an oxidation-reduction reaction is. So a shortened form of this, instead of calling it an oxidation-reduction reaction, we usually call these redox reactions. So when you have a redox reaction, two things have to occur. You have to have oxidation and you have to have reduction. When oxidation occurs, an atom or ion loses electrons. When reduction occurs, the atom or ion gains electrons. So a little bit counterintuitive. So one thing you can use to remember is the phrase Leo says grr. So this will help us keep this situation straight. So Leo stands for loss of electrons is oxidation, gain of electrons is reduction. So again, Leo says grr stands for loss of electrons is oxidation, gain in electrons is reduction. So when you're trying to figure out if you have or you're dealing with a redox reaction, you have to track what are called oxidation numbers. So oxidation numbers are assigned to elements in a neutral compound or in a charged compound, and they will help us track what's going on with the electrons. So that's how we know if an atom or ion has gained electrons or lost electrons. So as we go through to learn how to do this, there's a couple overall rules we have to keep in mind. Now on your list in your notes, these are actually the last two things, but I want to bring these up first, and I think as we go through the rules, this will help make them make a little more sense. So if you're dealing with a compound, and the compound's neutral, the sum of all your oxidation numbers is going to equal 0. If you're dealing with a situation like a polyatomic ion, then the charge is going to be the charge on the ion, or the sum of the oxidation numbers is going to be the charge on the ion. Okay, and that'll make a little more sense as we go through this. So if it's a neutral compound, the sum of all these things has to equal 0. If it's a charged entity, then the sum has to equal whatever that overall charge is. So as you are going through and trying to figure out what the oxidation numbers are, there's a couple rules that we follow, and we assign these particular elements first using our rules, and then we use that to kind of fill in the ones that we don't have rules for. So if you have an element by itself, the oxidation number is 0. So if I have sodium all by itself, sodium's oxidation number is 0. And by convention, we usually write those oxidation numbers at the top. Even if I have something like O2, that would still be an oxidation number of 0. If you have a monatomic ion, so a single ion with a charge, it's going to be the same as its charge. So if I have Na+, the oxidation number of Na+ is a +1. If I have O-2, the oxidation number of that substance is -2. The next rule is that oxygen, and actually before we do that, let's look at this first statement here. It says nonmetals tend to have negative oxidation numbers, but sometimes they can be positive when they're in certain compounds or ions, and we'll look at a couple examples of those. So oxygen is one of the first things we look for. So if it has oxygen, oxygen is almost always a -2. So we go ahead and assign it a -2. Even when it's in a compound, it's usually -2. The one exception is when you have hydrogen peroxide, or you have the peroxide ion. So hydrogen peroxide would be an example of where you would find that. In that case, oxygen has an oxidation number of -1. So let's look at two examples here. First example is H2O. So in H2O, oxygen would have an oxidation state, let me change color here, of -2. Okay, so oxygen's a -2. Now we go back to that original rule we said where the overall charge has to be 0. And that's how we can figure out what the other charge on the other atom is in a compound. So we're going to take the oxidation number times the subscript, in this case the subscript is 1, so that's a -2. So we know overall that has to give us a 0. So that means hydrogen's overall charge that it contributes has to be a +2. So if it's a +2 and there's 2 of them, the oxidation number that hydrogen would have to have is a +1. So in this situation, hydrogen's a +1, oxygen's a -2. Our exception that we just talked about was hydrogen peroxide. When you have hydrogen peroxide, hydrogen is another one of those we're going to talk about in a minute that is usually the same compound, or usually the same oxidation state. So hydrogen is usually a +1. So if that's a +1, and there's 2 of them, that gives us a +2. We know that has to equal 0, so that means oxygen has to contribute a -2. The only way for oxygen to be a -2, if there's two of them, is for it to have a -1 oxidation state. And just to clarify, when we're looking at the oxidation states, we're looking at these numbers at the top. Those numbers at the bottom were just used to kind of calculate and figure out what our oxidation states are. Okay, so down here, here's our hydrogen rule. Hydrogen is -1 when it's bonded to a metal, +1 when it's bonded to a nonmetal. So our nonmetal examples are right here. So there's a nonmetal example and there's a nonmetal example as a +1. Hydrogen can also be a -1. So if it is bonded to a metal, like in this case, it would be a -1. And then again, we can use that to figure out what the other substance is. So if hydrogen is a -1 in this case, and there's one of them, this is a neutral compound, so overall it has to equal 0. That means sodium has to contribute a +1. Since there's one of them, that means sodium's a +1. So the oxidation numbers in this case, sodium's a +1, hydrogen's a -1. Okay? Now, if you don't understand this yet, that's okay. This usually takes a while. We're going to keep going and keep doing more examples here. Okay, so our next rule is fluorine always has an oxidation number of -1. So let's say I have NaF. So in NaF, my fluorine is going to be a -1. So that means that gives me a -1 down here. Overall charge has to be 0. So that means sodium has to contribute a +1. So that means sodium up here has to be a +1. So in this case, sodium's a +1, fluorine's a -1. The other halogens have oxidation numbers of -1s when they are negative, but they can have positive oxidation numbers if they're an oxyanion. So let's look at an example of that. So other halogens, let's say like we have HCl. Okay, so in HCl, the Cl is a halogen, so it's going to be a -1. So basically that's the charge that it would have if you were assigning charges based on where it is on the periodic table. There's one of them, so that gives me a -1, has to equal 0. So then H, we know, has to be a +1, so that balances out the charge at the bottom. So oxidation numbers here, +1, -1. An example of when it's not a -1, if we have something like HClO4. Okay, now when you have more than just two, you're going to do the elements on the outside first. So we're going to figure out the elements on the outside and then use those to figure out the element in the middle. Okay, so oxygen we know is our -2, so this is not a case where we have peroxide. So -2 times 4 is -8. Again, neutral compound, so overall has a charge of 0. So now we're going to move over here to the hydrogen. Hydrogen is first in this case, so it's going to be a +1. There's only one of those, so that has to be a +1. So we're going to use this little situation down here to figure out what the chlorine is. So I have +1 from hydrogen, -8 from oxygen. So the only way this can total 0 is if this is a +7. So that means chlorine, since there's only one of them, is a +7. So that's an example of when halogens could have a potentially positive and kind of a weird number compared to what we're used to. So again, the oxidation numbers are those things at the top. Okay, so we're going to do a couple more examples here. So we want to determine the oxidation state of sulfur in each of the following, and in the process we will end up figuring out the oxidation states of all of them. So we're going to start with the ones we know. So on this one up here, hydrogen we know is a +1. There's two of them, so that means that that contributes a +2. It has to equal 0, so that means sulfur in this case is going to be a -2. So sulfur would have a -2 in that situation. My next one, S8, this is just an element by itself without a charge. So S in this case would have an oxidation state of 0. Down here, where I'm going to start with my halogen, so that's a -1. There's two of those, so that gives me a -2. I know it has to equal 0, so sulfur has to be a +2, and that'll balance out to 0. Okay, so sulfur in this case is a +2. Okay, here's one that has 3 elements, so I'm going to start with oxygen. So my oxygen contributes a -8, has to balance to 0. I'm going to go to the other side, and if you have metals on the left, then you're just going to assign those whatever the charges they would normally have. So sodium's normally a +1 because it's in group 1, so I'm going to assign it a +1. There's 2 of those, so that gives me a +2. So in order for this to balance to 0, sulfur has to contribute a +6. So since there's only one of them, it would have a +6 charge. Okay, my last example here deals with a charged substance. So I'm going to start the same way as before. So I have oxygen as a -2, and there's 4 of those, so that contributes a -8. Now the difference here is going to be a result of this charge here. So instead of this equaling 0, now it has to equal -2, and that's because this compound as a whole has a -2 charge. So we have to use that -2 when we're calculating our oxidation numbers. So if overall has to have a charge of -2, that means sulfur in this case could only be a +6. So that gives me sulfur. Okay? All right, we're going to do one more set of examples. So if you want to watch another set, you can go ahead. If not, you can skip forward here. Okay, so this one in your notes it says only look for the one that's in bold, but we're going to go ahead and do all of them just for some more practice here. So in this case, this is where hydrogen is combined with a metal, and I think we actually did this one earlier. So if hydrogen's with a metal, it's actually a -1 instead of a +1. So that gives me a -1. Compound is neutral, so it has to equal 0, which means sodium has to be a +1. Second example, oxygen, I'm going to assign -2, so that gives me a -14. And I know that overall it has to equal a -2 because this is another charged compound instead of a neutral compound like the last example we did. So that means that chromium has to contribute a charge of +12. Now since there's 2 of them here, that means the individual oxidation state on the chromium is a +6. Next example, tin bromide. This is the halogen. The halogen is the last element in the compound, so we're going to assign it its normal number, -1. So this is a -4, so that gives me a overall charge of 0. So that means my tin up here has to be a +4. Last example, barium oxide, oxygen -2. That gives me a -4, has to equal 0 because it's neutral, so that means that barium has to be a +4. Okay, and we'll do more practice with this in class. If it's still not clicking, we can do some more practice. It just takes a little bit of time to get used to if it still doesn't make sense. Okay, so the application of this then allows us to figure out whether or not we have an oxidation-reduction reaction. So single replacement reactions or displacement reactions, which is just another term for them, ions oxidize an element. So these are oxidation-reduction reactions. So what we normally referred to as a single replacement reaction in honors chem, we can now refer to those as redox reactions. So the element is oxidized and the ion is reduced. So we're going to kind of track the changes in one of these so we can see how this happens. So all of those reactions you did today in class, the ones that actually were reactions were redox reactions where there were electrons being transferred. So if we look at this example here, this was actually one of the things you did in class. You had silver nitrate and copper metal. So what happens is the copper goes from a copper to a +2. So the copper loses electrons, and then the silver goes from a +1 to silver metal, it gains electrons. So when we are tracking oxidation numbers here to figure out if we do have an oxidation reduction, this is kind of how we do it. So copper we go through first and put the oxidation numbers on. So copper here is a 0. Silver is a +1. Now when we're doing oxidation states, we don't worry about the coefficients. All we care about is the charge on that individual ion by itself. Then on the other side, copper +2 has an oxidation state of +2, and then silver over here by itself has an oxidation state of 0. So this is why you can't cancel an ion out with an element. So in this case, the oxidation numbers are different. They're different substances. So you can't cancel something that has a charge with something that doesn't have a charge. So then once you've done that, now you're going to track what's going on. So in this case, copper went from a 0 to a +2. Okay, so for something to go from a 0 to a +2 charge, it has lost electrons. So loss of electrons, we said, is oxidation. So copper was oxidized. Silver, change color here, silver goes from a +1 to a 0. So for silver to go from a +1 to a 0 charge, it had to gain electrons. So if it gains electrons, it was reduced. So this is an oxidation-reduction reaction because we have both. So the only way you can label it as such is you have to have something oxidized, something reduced. So copper went from a 0 to a +2, so it lost electrons. It now has more positive charges than negative, so it was oxidized. Silver went from a +1 to a 0. It gained electrons, and again, electrons are the only thing that can be transferred here. It gained electrons to balance that charge out, and it went to a charge of 0 and it became a solid. So in solution, what this looks like is you start out with the copper and the silver nitrate ions. Those silver nitrate ions take the electrons from the copper and become silver metal, and then those copper atoms become copper ions in solution. And that's why you kind of see this blue color starting to appear. And you can also see that little flaky stuff on that piece of copper metal. That's the silver metal that is coming out of solution. Okay, so this says to write the equation for the reaction of aluminum with hydrobromic acid. What is oxidized in the reaction? So we're going to write these just like we did before. And like I said, these are basically single replacement reactions, just like what we did before. So aluminum reacts with HBr. So this is a single replacement reaction. So aluminum is going to combine with bromine because aluminum is a positive charge. So this is going to be AlBr3. And then the hydrogen is going to come out by itself, but it has to be H2 because that's one of our Brinkelhoffs. So then when we do that, we have to balance this. So when we balance this, we end up with 2Al, 6HBr, 2AlBr3, and 3H2. So that's our overall balanced equation. So now what we want to do is look at our oxidation numbers for everything. So I'm going to start with aluminum. Aluminum, metal by itself, oxidation number of 0. In this compound here, I'm going to start with bromine. Bromine's a -1, neutral compound, means H is a +1. On the other side, bromine, still a -1, but there's 3 of them, so that means aluminum has to be a +3. So again, all I'm doing here is what I just got finished doing in those other example problems. I'm just skipping the step where I put the line underneath and total them up. So I'm kind of doing that in my head as we go here. And then hydrogen goes to a 0 because it's hydrogen by itself. Okay, so now what we can do is track what's happening to the electrons. So aluminum goes from a 0 to a +3. So if it goes from 0 to +3, it has lost electrons. So a loss of electrons means that aluminum was oxidized. On the other hand, hydrogen, actually let's look at bromine first. Bromine's a -1 here, and it's also a -1 here. So bromine didn't change at all, and that's entirely possible to have substances whose oxidation numbers don't change. So bromine we're just not going to worry about. Hydrogen though went from a +1 to a 0. So for it to go from a +1 to a 0, it had to gain electrons. So a gain of electrons means hydrogen was reduced. Okay, so let's do one more example at the bottom. You need to see another one. This one we have magnesium and cobalt 2 sulfate, so COSO4. Again, simple single replacement reaction. So we get magnesium sulfate and cobalt by itself. Okay, so we're going to start by assigning oxidation numbers to everything. So magnesium, element by itself, gets a 0. Oxygen, -2. Cobalt, on the other hand, is a +2. And then to get that in the middle, we'll go ahead and do that on this one. So this is a -8, and this is a +2. So since this is neutral, that means sulfur has to be a +6. Okay, so then on the other side, oxygen's a -2, -8. Magnesium's a +2. So that means sulfur is still a +6 over here. And then cobalt, element by itself on the side, goes to 0. Okay, so now we're going to track and see what happened to our electrons. So magnesium went from 0 to +2. So if it went from 0 to +2, that means it lost electrons, so it was oxidized. Oxygen, notice, stayed the same. So oxygen's still a -2, which is fine. Sulfur stayed the same, still a +6. But then if we look at our other substance, cobalt went from a +2 to a 0. So for it to go +2 to 0, that means it had to gain electrons, which makes it reduced. Okay, the last thing we want to look at in terms of oxidation reductions, and this relates to what you did in class, is the activity series. So metals have a pattern of reactivity that's exhibited when they react with each other. So we can list these metals in order of decreasing ease of oxidation. So what this does is this allows us to predict whether or not a reaction will occur when you mix two things together. Okay, so the metals at the top are called active metals, and if you look at the metals that are at the top of this activity series, you're going to recognize those as things that are very reactive. The metals at the bottom are called noble metals. Again, you'll recognize that they are things that are usually found in pure form. So when you're trying to decide if a reaction will occur, a metal in the series can only be oxidized by a metal ion below it. Okay, so what that means is when you're looking at this oxidation table, or this activity series, the only way a reaction will occur is if the metal is above where the ion is. So cobalt will react with compounds of anything below it. So cobalt will react with, say, nickel nitrate or tin nitrate or lead nitrate. It won't react with ions that are above it. So a metal can be oxidized by an ion below it. Okay, so we'll go through and do a couple example problems here to show that. Okay, I think what I'm going to do here, actually we'll go to the next page and we'll come back. Okay, so this one says, will aqueous solution of iron 2 chloride oxidize magnesium metal? If so, write the balanced equation. So what we're looking for, we have iron, and I'm going to go ahead and write this on here so we can kind of visualize what's going on. So we have iron chloride, so FeCl2. Will this react with magnesium metal? Okay, so what we're trying to decide right now is, will that reaction occur, or will all that stuff just sit in the container and you won't have any reaction at all? So to do this, we're going to compare magnesium to the iron ion, so Fe plus 2. So when we go to our activity series, those are the two things we're looking for. We're going to look at magnesium, and we're going to see if the iron ion is below it. Okay, so I'm going to skip back to this other page here and look back at our activity series. Okay, so iron, my metal again was magnesium. So here's magnesium. And then I'm going to look over here for my ions. So if I go down there, here's my iron ion. So since the ion is below the metal, that means you will have a reaction. So the reaction will occur. Okay, again, the metal or the ion is below the metal by itself. So this is the metal, ion is below it, that means the reaction will occur. Okay, so let's go back to our next page and go ahead and finish writing that. Okay, so FeCl2 plus Mg. So again, single replacement reaction, so I get MgCl2 plus Fe. Okay, and this one ends up being balanced the way it is. Okay, my last question here then is, which of the following metals will be oxidized by lead nitrate? So oxidized, again, that means which of the following metals will, we could also say, will react with lead nitrate. So what we're looking for is we're going to look for each of these metals, and then we're going to look for the lead, the Pb plus 2 ion. And again, if the ion is below them, then that reaction will occur. Okay, so to do this one again, I'm going to go back to my activity series here. Okay, so you can work off your notes, and then I'm going to do this straight from here. So my ion again was lead PbNO3 2. Okay, so this is my ion down here, so this is what I'm looking for. So what I'm going to do now is find those three metals, and we're going to compare and see if that reaction would occur. Okay, so my first one was zinc. Okay, so here's zinc. So zinc is up here, the ion is below it, so yes, this would have a reaction. Okay, my next example here is copper. So here's copper, here's my ion. So notice in this case, lead is above copper. So for copper, this would be a no. So that reaction would not occur. Last example is iron. So here's iron. Lead is below it. So for iron, Fe, That would be yes. So again, for a reaction to occur, the metal has to be above the metal ion. So zinc was a yes because lead was below it. Iron was a yes because lead was below it. Copper was a no because lead was above it.